Okay, so this video is going to be about the Mycielski construction, which is really important. It's a concept that was originally taught in Lecture 9, but we thought it needed some added explanation and some provided reasoning behind why the chromatic number must increase to t plus 1 from t when we increase the vertex size from n to 2n plus 1. So the Mycielski construction is very convenient in the way that it's built. It allows for the reasoning behind the chromatic number increase to be seen really well. So what we're going to do is we're going to begin with an original graph G, which will just be represented with an ellipse here. The specific nature of the graph is not extremely important, but rather the vertex size of that graph is. So we will label this graph G, and G has n vertices, so we will say size of n, rather we can just say vertex size of n. So again, the Mycielski construction is then going to see what happens when we increase this vertex size of the original graph G from n to 2n plus 1, what happens to the chromatic number? And so if the chromatic number is x, or chi of G, we're going to say that it's equal to t. So this graph G has t colors. So now we're going to increase the vertex size from n to 2n plus 1. So we will say increase vertex size from n to 2n plus 1. And many ask, how are we going to actually do this? So what's convenient about the Mycielski construction, really genius about it, is we are just going to have a set of independent points. We're going to call this set Y. And it's going to have n vertices. So if there are n vertices in the original graph G, and there are n vertices in the new independent set Y, which is listed above the graph G, we then have 2n vertices in total of our new graph, which encompasses both the independent set and the original graph G. And right now you're probably thinking, well, there's two components of this graph. We will eventually make sure that they are, this is one component in total, and how we actually connect these vertices to a vertex in G is extremely important. That's what we're going to do next. Beforehand, I'm going to label this. I'm going to label the count of the vertices to show this is 1. This is the second vertex, and then this goes all the way up to n vertices. So now we satisfy this condition for the new graph, or at least satisfy part of it of having this 2n vertice count. But then we have this plus 1. And this is going to come in handy. And really, it's important that we pay attention to how we add this additional vertex. So what the Mycielski construction does is it says, let's put an additional vertex above or just around the independent set Y. I should go ahead and label this. So this is the independent set Y. And this new point that we add, this additional vertex, which satisfies the final vertex size of the new graph, 2n plus 1, this additional vertex we're going to call x naught. So we're going to call this x naught. And what's unique about x naught is we're going to make sure that it is adjacent to every single point in the independent set Y. Now, it's important to keep in mind that because this is an independent set Y, all the points, all the vertices within the set are non-adjacent. They have no edges connecting each other, and they are independent. So now we are going to, and make sure I get the segment tool, we're going to connect all of the vertices in the independent set Y to this additional vertex x naught. So this is beginning the construction. So all these are connected. And the next step in the construction is going to go back to the original graph G and look at one of the vertices inside that graph. And what we're going to end up doing is we're going to call one of those vertices X, and we're going to specify a color. And so how the Mycielski construction proceeds proceeds is really a color modification process. So we really start that process off by labeling this point that I'm talking about, this vertex NG. So this vertex is X. X is any ordinary vertex within any ordinary graph G. But what we're going to do is we're going to introduce a concept that really hasn't been introduced prior to Lecture 9, but by Lecture 16 through 21, the ones that we're on right now, really this is a concept that should be understandable, very comprehensible to anyone. What we're going to do is we're going to specify a neighborhood of X. So a neighborhood of X is a set of points that are all adjacent to X. So what we're going to do is just set up those points. And so I'm going to really quickly do it by just having segments, but the endpoint of all these segments will be that point in the neighborhood of X. This is the neighborhood of X. So we're going to proceed by assigning a color. And so it's really important to remember that this has a T colors. But what we're going to do is we're going to assign a color to X naught. And we are going to say that that color is alpha. And so alpha will be our new color. Let's find alpha. And alpha is a color of X naught where alpha is an element of the range of possible colors, which range from 1 to T. So this is just important. And it's important to specify this because it helps later on. So we're going to touch on the concept of coloring specific vertices in just a little bit. But the next thing we need to do is connect these two components. So right now we have this new graph, which consists of everything on this page. But there's two components. We need to make sure that the graph is just one component. And so how we connect these two components is pretty important. What we're going to do is if we connect one of these vertices that's located in the independent set Y to a vertex that's in the neighborhood of X, then this vertex in the independent set Y will not be adjacent. It will be non-adjacent to the vertex X, which is what we need to maintain. The reason why we need to maintain it is if they were adjacent, they would have to have different colors. We'd be increasing the color, the chromatic number of the graph beyond T. And remember, the goal of the Mycielski construction is to attempt to show that the new graph with 2n plus 1 vertices can have T colorings. But at the very end of the Mycielski construction, we will eventually find that we have to have T plus 1 colorings. So what we're going to do is we're now going to connect these points, these vertices in the independent set Y, to a corresponding vertex in the neighborhood of X. And so each of these points in the independent set, and each of these vertices in the independent set Y will have to be connected with an edge to a point in the vertex in the neighborhood of X. So now that we have these connected, and I'm not going to do it for more than one because it's the same thing, and as you can see already, the crossover, the amount of edges that we're dealing with gets pretty hefty. So now that we've connected all the vertices that are located in the neighborhood of X to at least one of the vertices in the independent set Y, we can start defining some basic terminology here. This vertex in the independent set Y we call the mate of the vertex X in the original graph G. They are mates because they are not adjacent. So if we look, there's first an edge connecting the vertex in the independent set Y to a vertex in the neighborhood of x, and then an edge connecting the neighborhood of the vertex in the neighborhood of x to the vertex x. So it's really important that we get down this terminology right now. These are mates. So this mate of x we will call y sub x. And I will label that here. So this will be y sub x. And so now that we have this mate set up for the vertex x, we can start looking at how we go about coloring the graph. So essentially, if this were to be repeated for all the points x in the graph G, for all the vertices in the independent set y, we would have our complete new graph. And then we would start the process of coloring. And that would prove whether or not, if we increase the vertex size from n to 2n plus 1, whether or not the chromatic number would increase from t to t plus 1, or if it would just remain t. And by conducting the Mycielski construction all the way through, we eventually find out that the chromatic number must increase to t plus 1 colors. And so what we can do in addition to this, what we're going to do is, before we proceed with coloring, we're going to go over the concept of mates. So we will have this 5 cycle. And in this 5 cycle, so this has n vertices or 5 vertices. And then to increase the number of vertices to 2n, we will have 5 vertices that are independent above. And then each of these will be set up as mates to the other. So this can get fairly convoluted without curved edges, and that's what we're dealing with here. So bear with me, but this should make more sense later on. So what we're going to do is we're going to start by connecting each of these points, each of these vertices, and we're going to have these be the mates. So these are going to be the mates. So we start this by saying that this vertex right here will be the mate of this one. So this vertex right here is the mate of this vertex, which means that it cannot be adjacent to it. So instead, we're just going to connect the other vertices around it. And let me make sure. There we go. And then the same thing. This vertex will be the mate of this vertex. So we will say that here, or rather actually this vertex, one right here, will be the mate of this vertex across. So where we're going, or this vertex right here. So we're going to cross here and cross here, working around. And then this vertex right here will be the mate of this vertex. So this one connect here, and this one will connect here. This vertex right here, this fourth vertex, will connect to here, because its mate is the one to the right, and then it will connect down here. And then this vertex will connect here and here. And normally these would wrap around. But the concept of mates, walking through this is just to further provide further clarification for why this vertex in the independent set y is the mate of the vertex x. And again, it has to do with adjacency or lack thereof. The vertex x is not adjacent to this point y sub x, and y sub x is the mate. So this is part 1 of the Mycielski construction. Part 2 in the video, part 2 for the Mycielski construction, we'll go over the procedure for coloring, and how the procedure for coloring eventually reveals that no matter how much we try, by proceeding through the rest of the Mycielski construction, we will prove by contradiction that the chromatic number will indeed increase to t plus 1 when the vertex size increases from n to 2n plus 1.